Okay, all right, let's get started. So before we do a recap of what happened last week, the first thing is labs. So, labs was, there's no labs this week. For next week, we'll start doing an introductory session. So it'll be very quick next week, but we'll have we'll basically do a dry run to see that you can install the software for next week. Okay, so there's no labs. This week, we'll have introduction to labs. Right, so there'll be more information coming shortly. So I'll send an email with the software you have to install. The software is a free software, but you do have to install it before the lab. Okay, so that will follow later today or tomorrow. All right, so the things for you guys to do is figure out your lab groups, basically. Okay, so I believe you can see who's in your lab session on Canvas. Right, so go to your session and try to form groups of 2 or 3. Okay, if you cannot, then that's fine. Then we'll sort it out next week. The TAs will sort out them. But then if you can find your own groups, that'll be easier for everybody. Any questions about that, about the labs?
How do you want us to let you know what groups we want?
Just tell the TAs next week. So so there's not that many people in your session. So the TAs will ask, who's in your group. Just tell them. Any other questions?
Where on Canvas are we supposed to see which labs people?
I believe if you go to the class website, you click under people, you'll see there's a list of all the students in the class, and you can sort that by the lab session, like AA, AB, and things like that.
Okay, thank you.
Yeah, so if you don't find the group, that's fine. Just show up to your lab session, and TAs can assign groups then. But if you have some predetermined group you want, then you can form your own groups. Okay, so the labs will run, so next week is introduction, so everybody will show up. Then afterwards, there will be bi-weekly labs. And it's a computer simulation based lab. So you do a bunch of experiments, changing different values and seeing what can happen. And then you write a lab report, right? So the report is 1 report per group. Right? So you as a group, you write 3 reports. That'll be 25% of the grades. And the expectation is you will show up to the lab, right? So the labs are synchronous, right? So be no credit for people who do not show up to their labs. Okay? So the class, you don't have to show up to every class, but for labs, you are expected to show up to each lab. Otherwise, there's just not. Right? So that's the expectation we have. If you cannot show up to the lab for some reason, then do let me and TS know. But the expectation is you show up to your own lab session.
So are the reports due at the beginning of each lab?
They'll be due 1 week after. So you do 2 labs. You do a lab every 2 weeks. So you do a lab and you write a report. That's for we'll do the week after the lab. Any other questions? Okay, so that's that for labs. The labs are relatively faster this time because it's virtual. So it's for less time on the labs compared to the labs before for this year. Okay. All right, so if some of you are, for example, so for people who's listening to this as a recorded lecture, please let me know if you cannot show up to the labs at the same time. Okay, please communicate with me, right? So other than that, the first homework is out. It's due this Thursday, so take a look. Right, then if no other questions, let's do a recap of what we did last time, right? So last time, what we did is we, look at, for example, a voltage or current, time domain, right? So last time we started by looking at a time domain signal of a voltage, say, in this form, sine omega t plus theta. Okay, so if you start with a waveform like this, you start with this waveform, then we quickly figure out that you can put this through any combination of circuits, for example, either a resistor, a capacitor, or an inductor. Then the current, right? So if you look at what the current you resolve, the current is still some sinusoid, has the same frequency. It's still a sinusoid. Right. So then our goal now becomes, let's not write the sine or cosine every time, right? Since everything is sine and cosine with the same frequency. So the only two things we care about is the RMS voltage or RMS value of the signal and the phase offset. So that's the only two things we care about. So then we introduce phasors, for example, things like this. This is a magnitude and angle, right? So this is our phasor. Then you can represent all these components with phasors. So here, so we're going to denote a generic impedance by X, a phasor X, right? So here X is some impedance value. Okay, there's some impedance value. Then if you have a resistor, here X bar is just R, this purely real value of inductor. Here X bar is XL, let's say angle 90 degrees. Right, this is a purely imaginary impedance. Then we have a capacitor, we have X bar, this is XC angle minus 90. Also a purely complex, a purely imaginary impedance. Any questions so far? All right, good. Right, so this gives us a way to talk about impedance, voltage, and current. Right, so this is some basic quantities in circuit analysis. But we care more than just about voltage and current, right? This is a power analysis class. So for a power system class, what you care is about the power you get from this circuit. Okay. So now the question is, what about power? Okay, what happens to power? What we want to write as power equals to voltage times current. Right? This is something we want to write. Right? So if we form a complex value, if we form a circuit, then we want to think of the power of the circuit as voltage times current. That's the standard equation we want to use. The problem with here is that we have complex numbers, right? So you need to be careful when you work with complex numbers. Be careful. What does this multiplication mean? For example, complex numbers. And the second is we said everything, current and voltage. If you look at the time domain signal, as sinusoid with some given frequency. So we don't have to worry about the frequency. Now the question is, what happens to power, right? Is there the same case for power? It's the same case for power. So the question is, can we write? For example, power equals to the voltage phasor times the current phasor? Is it possible to write this? Any guess? For people who remember complex circuits, is power actually voltage times current?
No,
No. So what is it actually? Anybody remember?
it's the V max times the cosine stuff with the phase shift, right? Times the
Right.
current.
Right, but that's too hard to work with, right? So I don't want to write the sine wave multiplication every time, right? So when we talk about, your computer is, let's say your computer is plugged into the wall and, 100 megawatt of power is going into your computer. We want to talk about something like 100 megawatt, not 100 times sine of 60 hertz plus some phase, right? That's not, we want to talk about this power as a single number. So the nice thing about phasor notation is I can talk about voltage, current, and impedance as complex numbers, not functions. I don't want to deal with functions. Then how about power? So is it true that once we get the voltage and current down to a complex number, we just multiply the complex number together? And so we get power? Right. Can I still ignore the fact I have a function, right? It's actually some sine times another sine function, but let's ignore it. Is it true that I just need to talk about both multiplication and complex numbers? Right, so this is actually not quite true, okay? So this is not right. Okay, so this is not correct. This is not the way it turns out for it to work. Okay, so that's another reason you should be a little bit careful when you talk about complex numbers. So going to, so this class, when we start, we'll see why this is not the way the power equation is, right? So the actual equation, so the true equation, right? So the equation is we want to think about power as V times I star. Okay, where this star, this is a complex conjugate. This is a complex conjugate of the current. Right, so we'll do some calculations and let's see why this is the case. Okay, why does it make sense to talk about power in this case? Okay, all right, so let's look at, the simplest case. Let's look at, so how do we get to this equation, right? And what does this equation mean? This is a complex number, so how do you interpret different parts of the complex number? So the way you interpret, the way we get to this sort of complex power equation is you just look at what happens when you have a resistor, inductor, and capacitor, and see what happens when you just, again, multiply the time domain waveforms together and try to parse that result and try to relate that to the what happens when you multiply two complex numbers together. Okay, so that's a goal we want to have. Right, so then if you look at the waveform across a resistor, right? So let's look at waveform across a resistor. Then let's say what would happen, right? So let's say if you assume that the cross a resistor, what we have is P of T, right? So this is, or rho of T, as written in books. So this is the instantaneous power. This is really the time domain power. This is, if you take oscilloscope again to your wall and measure the power, you measure this type of power. So this is always true. Vt times it, this is always correct. So let's say we have something like V max sine omega t, I max sine omega t minus theta. We multiply this thing together. A very nice thing happens is you can do a bunch of trig identities. This turns out to be V times I times cosine of theta minus cosine of 2 omega t minus theta. So if you just multiply them together, you get this notation where V is V max is the RMS values of all these. V and I are the RMS values of the sinusoid. So you get this equation. Then for a resistor, theta equal to 0. Okay, theta equal to 0. Then what we have is rho of t simply V times I my 1 minus cosine 2 omega t. Any question up thinking now? This is for a resistor, since there's no angle difference between voltage and current when you pass them through a resistor. This is the result you get when you multiply them together. Okay, so this is a resistor, but remember when we have a resistor, right? So some of you, there's a sort of common misconception that when you talk about AC power, the power across resistor is constant. That's not quite true. The power still goes up and down, actually. The power still goes up and down. You have this cosine to omega t term that does not go away, even for a resistor. Right? This doesn't go away for a resistor. But simply, this is a waveform we'll take. So we're going to say, right? So we're going to identify this sort of time varying waveform with a resistor. Okay, so it doesn't mean the power across resistor is constant. However, it just means that they're still varying. There's still time varying power, but we're going to identify this whole sort of time varying waveform as a power across resistor. Okay, so this is still varying, but we're going to assign a number. We're going to assign a name to this. Okay, so let's assign a name to this called the P. Okay, so we're going to assign anything that looks like VI times 1 minus cosine 2 omega t. We're going to assign this, call this P. Identify this thing with P. So we're going to look at this, right? So we're going to look at this resistors. Then if you look at complex domain, right? So if you look at complex domain, you have some resistor with value R. Then if you look at voltage, right? So the reason I need a star again here is I want to assign this. I want to assign a number. I want to associate this VI times 1 minus cosine 2 omega t with a number, right? So, but then if you look at, let's say I have some voltage. Phasor is V angle theta. I have some current, now is V over R angle theta. Okay? So if you just take V times I, it doesn't look very correct, right? The reason if you just take V times I, it doesn't look very correct is, so what do you get if you just do a V times I in this type of complex multiplication? What's V times I? V is V angle theta, I is V over R angle theta. What's a phasor multiplication result when you multiply V by I?
2 phasor, 2 theta.
Q theta, right? You have V squared over R angle 2 theta. Okay, you have angle 2 theta. Well, this really doesn't make sense. Because if you look at this equation, there's no theta. There's no theta anywhere in this equation. But if you just do V times I, there is some 2 theta that's hanging around. But theta should disappear, right? Theta should not be there. We'll do this multiplication. Okay, so this is incorrect, right? So this is incorrect because I don't want theta. There's no theta that shows up in the time domain waveform. So theta should not show up when I multiply phases together. Okay, this doesn't, the theta should cancel somehow. So then what we have is, we'll look at, so power is really what we look at as VI star. This is called complex conjugate. So for complex conjugate, what you do is you basically, it's the same magnitude, you reverse the angle, right? You reverse the angle. Or if you have the rectangular form, then this is A minus JB. Okay. Then, or this is, in some computer programs, this is just written as conjugate of A plus JB. And sometimes you'll see this command, conjugate. Right? So this makes more sense. This makes more sense, right? Because VI conjugate is V angle theta, V over R angle minus theta. And then this thing cancels, right? And then the angle cancels. The angle cancels out and get a V over 2 over R, or just the magnitude multiply each other. So this is similar to the sort of DC circuit case we had before, right? So power over resistor is voltage times current. Okay, so that's the reason where this star comes from. We want the angle to work out correctly. Any questions with this calculation?
Yeah, where you drew the red X, why didn't we want theta to show up there?
Right, so if you look at the time domain formulation, right? If you have a, let's see. Okay, let me be more explicit with this. Let me be more explicit with this. So this is the side. Okay? So if you have voltage, so let's say we have a generic angle. Okay, let's say we have, this is V max sine omega t. Right, so let's say I have some angle associated with the voltage, right? Let's say I have some angle associated with this voltage. Then, if I pass this through a resistor, I have I of t, V max over R sine t plus. Right, so we have this term. We have the same angle showing up here, right? I have the same angle. So there is, now if you look at the phasor notation, if you look at the, okay, so let me be more careful with this notation for angles. And if you look at the phasor notation for V, right? Right, okay, so this is our time domain. Now we can multiply Vt times It together, right? So we can multiply those two numbers together. When you multiply them together, you get V max squared over R sine omega t plus theta, this whole thing squared. Okay. So now you can do the trig identity trick. Okay, so you want to write it. You want to write it as before. You want to write it as with the same formula as before. You want to write this as V max. So this is V squared over R. 1 minus, right? This is the same Notation as before, this is 1 minus. Turns out this is cosine 2 omega t. So you get this notation, right? You get this notation. But now if you look at this term, this cosine 2 omega t plus 2 theta, you compare with cosine of 2 omega t, right? So what's the difference between cosine 2 omega t and plus 2 theta with a shift of 2 theta versus cosine 2 omega t? It's basically you have this waveform. Right, and you can shift this thing around. You can shift this waveform around. Any question up to now?
So in this case, they both the same.
So you can shift this waveform around. When you shift this waveform around, what happens is one, it's the same average. There's no impact on this average, right? You just phase shift. Second, this is actually the reference. And now basically, since we're averaging, remember we're averaging, we're looking at basically the power. So it's the same average power. And also here as this, also the same up to a reference angle, up to a shifting reference. So then the idea is, again, if you measure this waveform in the wall, you actually cannot tell what the shift is. Because all you do is you get a waveform that looks exactly the same, except up to an arbitrary angle shift, arbitrary shifting time. But since it's the same repetitive waveform over and over again, you actually cannot tell what the reference is anyways. Okay, so if you take oscilloscope again, if you measure the waveform, as will look exactly the same. Right? The two waveform will look exactly the same on your on the scope that you have. Okay, so there's no change in the instantaneous power. There's no difference in the power. Okay, any other questions? So this is something you want to distinguish between this and say an inductor, okay, or a capacitor. If you have a capacitor and you take the oscilloscope, you would not measure this waveform. But since we have a resistor, we'll measure this waveform and they'll be the same waveform. Okay, up to this arbitrary shift of the origin. Okay.
Thank you.
All right. Okay, so this is the case for a resistor, right? So the idea to remember is we'll identify what we want is we basically want to identify this 1 minus cosine 2 omega t term with a real number, Then let's look at when we have with a inductor or capacitor, right? What changes with this? So if you look at the purely inductive load, right? Now there is an angle difference. So basically what you do is you take this. So what you do is you take this equation and you plug in some data into this. Okay, you plug another data in. You plug an angle difference into this. So here, let's say you have an angle difference of 90 degrees per inductor. You multiply them out. What is cosine of 90 degrees? Remember what's cosine of 90? Right,
Zero.
0. This is 0. And then if you shift the cosine by 90 degrees, what? So if you shift a cosine by 90 degrees in phase, what actually do you get?
A sine.
You get a sine, right? So the way to this actually becomes minus VI sine 2 omega t. Okay? This becomes minus VI sine 2 omega t. So this is different than a resistor, right? Because resistor has a cosine 2 omega t term. This thing has a sine 2 omega t term. Okay? So this is another thing we want to differentiate between the resistor and the inductor. As resistor has this 1 minus cosine 2 omega t, this thing has sine 2 omega t. So a thing you recognize as this is 0 average. Okay, so if you integrate this power over a period, you get 0, which makes sense because inductor stores power, right? Cannot create power, but can store power. So this is just inductor sloshing the power back and forth. So just sloshing this power back and forth. Similarly, if you look at a capacitor, this is minus, this is 0, this is minus sine 2 omega t. So this is VI sine of 2 omega t. Again, this is 0 average. Okay, this is 0 average. Okay, so this basically tells us when you have some power, you have one part that's associated with this sort of 1 minus cos 2 omega t term. Another part that's associated with the sine 2 omega t term. Okay, so in general, when you have a complex load, what will happen is you want to write this as something multiplied by 1 minus cosine 2 omega t plus something multiplied by sine times 2 omega t. This is what you want to write the two things as. And when you write it in this form, we want to basically identify, give a name to this bracket, and give a name to this bracket. Okay, so that's our goal. As we said, a resistor is different than inductor. So let's look at what happens when you get a resistor. So this is 1 minus cosine 2 omega t term. Let's look at what happens when you get a inductor or capacitor. This is a sine 2 omega t term. So let's assign, so when you have a generic complex load, then the term that's in front of this 1 minus cosine 2 omega t should be associated with a resistor. Term in front of sine 2 omega t should be associated with a inductor or capacitive load. Okay, so this is the idea. Right, so you want to get fancy, this is basically, I want two basis vectors. Okay, on an orthogonal basis, here one is 1 minus cosine 2 omega t, another is sine 2 omega t. And assign a coefficient to each basis when they have a complex load. And then the mass calculation basically boils down to this. Okay, so let's look at both something called real power and something called the reactive power, a real or active power. Okay. So if you look at this equation, you can always write this equation as the following. Okay, so let's write this equation out. Cosine theta minus VI. I'm going to do a double angle expansion, cosine theta, cosine 2 omega t, plus sine theta, sine 2 omega t. Okay, so this is our double angle expansion. We're going to collect the terms. So we have VI cosine theta 1 minus cosine 2 omega t minus VI sine theta sine 2 omega t. Okay. So again, this is the idea that you can write any power into these two brackets, right? Into this two linear combination of these two terms. Right? Then the first term is useful because it tells us what the average is, right? So this has 0 average, and this has an average of VI cosine theta, right? So this is what the average is, right? So cosine and sine average out to 0 over a period. So this is what we have, right? Okay. So then you want to identify, right? We call this, right? So this is, so this is called the real power. This thing that average out to be 0 is related to real power. This is related to the reactive power or imaginary part. To real or active power, it's the same thing. So the idea is you write this into two parts, VI cosine theta, 1 minus cosine 2 omega t, minus VI sine theta, sine 2 omega t. And this is called the active power P, and this is called the reactive power Q. Okay, so this is just names given to, these are just the names given to the two parts of it. Okay? And the idea is the active power is something that has an average, of non-zero, right? So the real power, active power, is the average amount. And then the reactive power is related to the oscillation, but it's not entirely the oscillation, right? It's basically the oscillation that relates to the sine part. Okay, so oscillation that's related to the sine of 2 omega t part, right? That's the idea we have when you write this power equations. Right, so any questions up until now?
I'm still a little bit confused about the reactive part.
Right, okay, so is this equation complete before naming a reactive power? Do I understand? Is the derivation of the equation clear?
Yeah, still confused about
Right,
it.
so you can write the equation as these two parts. Now I'm going to choose to call them different names, okay? So why do I call them these names? Well, the neat thing is, if now you look at VI conjugate or V, let's say V is angle 0, right, for simplicity. I as I angle, okay, I is angle, or let's say I is angle, right? Let's say, okay, so let's say, so V is V angle 0, I is lagging, so let's say this is I angle minus theta. Then VI star, this is VI angle theta. And if you do this trick, right? So this is this, if you expand this into real and imaginary part, this is VI cosine theta plus J VI sine theta. And this is plus J VI sine theta. Okay, and the neat thing is they line up with the coefficient in front, right? Now it comes to a question of what do we call it? Right? What name do we call these powers? So it's cool. Yeah, go ahead.
So for the currents, it's I negative theta, but how do you get VI is theta?
So this conjugate, right? Conjugate.
Oh, conjugate.
Conjugate, right? So you need to conjugate the current. The reason you need to conjugate the current is that's the way it works out. So if you don't conjugate the current, you have a wrong sign. So we need to do a current conjugate, right? We don't want the wrong sign to come up. Okay? So we need a conjugation, right? We need a conjugation. Okay? So this is a conjugate, and this is the way the sign works out. And the question is, what do you call this, right? So it's very clear, P is the average of this row of T, right? This is just one over T, 0 to T. If you integrate this, you get P, right? This is, if you just integrate this time domain waveform, you get, this is what P is. So this is sort of intuitively simple. This is, or intuitively more straightforward. This is what you call the active power, and we give it a unit of watt. Then the question is, this only captures one part of the waveform, right? My waveform has two parts. I have a sine to omega t term that somehow needs to show up in my representation, right? When I talk about power, I need to talk about this power somehow. Okay, so what name do I give to the power, right? What name do I give to this oscillation? So what do you think the sort of the most natural name is? Right? The reactive power is a little bit weird, so we just created that term called reactive power. Right? So before, since this was the imaginary part of this VI star, VI conjugate, we sometimes, right? So this before was called imaginary power, right? And P was called real power. And then Q was called imaginary power. And that's obviously not a good name, because imaginary power gives the idea that's not there, right? It's sort of not a physical phenomenon, it's something sort of mathematically created. That's not the case. You can't measure Q. It's sort of trivial to measure Q, because all you do is, you take oscilloscope, you look at what is the term in front of the sine to omega t. Okay, so it's quite trivial to measure Q. So imaginary power is not a good name. It's not a good name. So then we create a name, we call it reactive power. And this is the power that's in front of sine to omega t. That's represent the power going back and forth within the inductor and capacitors. That's just sort of the nature of this power. Okay, so this is just oscillation of power in the circuit. The reason you have oscillation is because you have inductors and capacitors. Okay. All right, so then to make sure we understand what this reactive power is, so it turns out for both inductor and capacitors, when you do the calculation, as something proportional, right? Something is coefficient multiplied by sine to omega t. Okay, so in this case, we do not necessarily need to differentiate, right? We can add and subtract the reactive power coming out of inductor and capacitor, because both of them varies with the same as proportional to sine to omega t. Okay, so that's the idea we have. Okay, so when you do this complex multiplication, you get two, right? So, or even do the time domain multiplication, you get two terms. When you do the complex multiplication, you also get two terms. We identify the one that carries the average with the real part of the complex power, called the active power. Then the imaginary part is identified with reactive power. Right? It's identified as reactive power. Okay, so that's the Q we have. Okay, that doesn't mean it's imaginary or it's not there. It's just something that has zero average, and turns out to have a waveform that's sine to omega t. Okay, that's sine to omega t. All right, so P is the average. Q is something that's proportional to oscillation. Right, so Q, this is oscillations. Okay. So that's a reason we want to use different units, right? We want to use different units because these units are useful to tell us what are we talking about, reactive power, or active power, or a combination. Okay. So the active power is just watts. Okay. That's the familiar unit of power. Then for reactive power, we just call it volt ampere, right? A volt times the ampere reactive. So you have VAR, kVAR, and VAR. This kind of names. Okay, so then before we take a break, let's do this. So to finish up this discussion, as we have complex power, and we have complex power, so we call this VI star. By definition, this is called S, and S is a complex number, and this is called complex power. And then again, this is written as, if you write it in rectangular form, this is P plus JQ. And this again is VI cosine theta plus JVI sine. This is so often in calculations, what you do is you write a very complicated circuit. You have a complex circuit. You figure out the voltage and the current, and then you plug into this equation, V times the conjugate of the current. And then you read off the real part and the imaginary part, right, as different powers. Any questions?
No question yet.
All right, okay, all right. So this is sort of the, if you want to remember the equation or the operational way of doing all those powers, this is the equation to remember. Okay, and make sure, right, for this equation, make sure you can do complex multiplication, right? Make sure you remember the conjugate. Remember the conjugate, conjugation on the current. Okay, so if you miss this conjugation, then all the math or subsequent math will be wrong when you're computing power. Okay, so this is important star, the star on the current is important to remember. All right, so then now, yeah, go ahead.
That star is only apply on the current part?
Only
not-
on the current, only on the current. Yeah, so let me be this, only on the current.
Thank you.
Yeah, so do remember, right? So this is by far the #1 mistake where people lose points on the midterm, as they forget to conjugate current, right? And I think, right, so every year 10% of the grade is due to people not conjugating this current, right? So please do conjugate this. So remember this formula, have the conjugation, then sort of mechanically, this is how all the calculations work. All right, okay, so now let's take a break. Let's take our 2-minute break. We'll come back at 3:30. We'll do some exercises of looking at these equations and okay. All right, so let's get back. Okay, so the complex power, right, is a complex number, right, has a real and imaginary part. So often what we want to do is we want to look at the magnitude of this power. Okay? So then the apparent power is simply the magnitude of the complex power. Right, so then this S, this is by definition called the apparent power. If you just take the complex power and look at the magnitude. And the magnitude, right, and the units for this just call something called a volt amperes. So you'll see kVA, MVA. So all of these are the apparent power ratings. Okay, so it has a unit of just a volt amp, a volt times amp. All right, since we don't know the sort of real and the imaginary parts of it, right? So it's not, we can't assign, for example, watts to this. So then we just create this unit. Right, so often when you buy an equipment rating, for example, if you look at a transformer, you have a rating of kVA or MVA. Right? That's for so how much apparent power can this thing handle. All right, then we can look at different types of loads, right? So if you have inductive loads, then here, what happens is your impedance. So if you together, you look at Z. Z has a positive imaginary part, and will turn out power looks similar form. This is XL, and this is S. Okay. So here we have a angle, we have Q equals to VI sine theta. This is theta. So this is what we have is this is larger than 0. Okay. So inductive loads, this means this load will consume reactive power. Right? So Q is positive. So a resistor consumes active power, inductive load consumes reactive power. And then for a capacitive load, you have the opposite situation. Right? The opposite situation, we have a negative. We have a negative imaginary part, so the power will also be negative. P, Q, S. And here we have Q as VI sine theta. This is less than 0 since the angle theta was less than 0. So this is something called that, for example. So this here we can say, since this is a negative number now, right? We can think of this as a capacitor producing, right? This is producing reactive power. So again, the quotation here is you should not think of reactive power production necessarily is the same as active power production. Right? So active power production, for example, can be turned into work or eventually becomes heat, right? So that's the active power production. For reactive power, whether it's consumption or production, right? Whether it's consumption or production, depends on the sign. But remember, in the time domain waveform, as a number that's multiplying sine to omega t. So it's 0 average, no matter what the sign is. Right? So it's more like a convention. We call one of them consuming, one of them producing. Right? So we need a way to talk about them. So by convention, we give this terminology. But really, you do not need to do work, right? You do not need, for example, a generator to provide this. You can put a capacitor in the ground and we'll give you reactive power. Okay, so that's just something to keep in mind when we talk about this terminologies. Right, so similarly, so to develop this further is, if you look at the Q, right, consumed by this, then this will turn out to have a very similar formula as, right? So if you just look at the reactive power part of this circuit, then this will be I squared times XL. Right, this I squared times XL, this is a consumption. Right, so this is a consumption or consumed by the inductor. Whereas for this, we have QC, this is, one thing about this is minus I squared XC. this is production. Okay, so you can cancel, right? You can cancel things fairly easily, right? You can cancel reactive power production or consumption by making the adding capacitors or inductors in the circuit. Okay, so reactive power as active power is conserved, but it's fairly easy to produce or consume it compared to active power, right? For example, we do not have a negative resistor, right? We don't have a negative resistor that will produce power, but we have for active power, but for reactive power, we have positive and negative things. Any questions?
So just to clarify, like
Right.
the negative and the positive of the reactive power is more of like a convention thing. Like inductors and capacitors are both like storing and releasing
Right.
energy. And like to me that doesn't, it seems like they just do it at like different times, I guess. So,
Right.
like,
Yeah. Right.
but the positive and negative is more of a convention thing for like our calculations, or
Yes, that's basically the intuitive feeling to have, right? So they store energy. They release at different time because one is a differentiation, right, for the inductor, one is the integral. So in the phasor form, one shifts the waveform by 90 degrees this way, one shifts the waveform 90 degrees this way. Right? So then they act in opposite ways, right? They're opposite to each other because they shift the waveform in two different directions. So what we want to do algebra, we want to assign plus or minus to them, right? So we call it production and consumption. But the English understanding of production for active power is sort of different than for reactive power. Right? So sort of keep this in mind, right? You would read things like, oh, I'm producing reactive power, I'm doing this, right? So sort of should have a little bit different mental picture than say producing active power.
cool, thank you.
Right. So you often see, people say, I install a solar cell, this solar cell can produce active and reactive power. Right. So then the question is, okay, where does the reactive power come from? Right. It actually comes from the phase shift, right? Or a capacitor somewhere in the cell. Right? So that's something to be aware of, right? So people say, reactive power is hard to understand intuitively. For us, it's just some oscillation, and the sign of reactive power tells us whether the oscillation is, right, whether it's for in phase with sine to omega t or it's 90 degrees out of phase. That's the sort of the only thing. So that's the important thing for us. All right. So yeah, go ahead.
Sorry. So can you elaborate why do we care about it? Because if I understand you correctly, and if I remember from 233, you said reactive power does no work. So it's not gonna power a house or circuit or anything like that. So why do we keep track of it, and what is the purpose of knowing what it is, and why do we care?
Right. Okay, good. That's a good question. We'll come to it later in this lecture. We'll come to this later lecture. Because turns out, even though reactive power does no work, it doesn't mean you can ignore it, right? So it's still part of the waveform. So something has to take this into account. And in a very short answer is reactive power does no work, but sometimes takes up some room. For example, your transformer have a rating that's on the apparent power, right? The transformer rating does not differentiate between active and reactive power. We'll see that when we get to a transformer, but it doesn't differentiate between these two, right? So that puts a limit on the apparent power. So if you have too much Q, then not enough room for P. Okay, so often P is something you want. Also, what happens is even though it does no work, it's still present in the system. So it's impact something like a voltage, right, which we care about. So I guess for you guys, can you think of the appliance in your home that has significant reactive power component to it? Right, so things in your home like your computer, your TV, your phone, your light bulb are all active power. But what has reactive power? What actually care about reactive power in your home? Or putting it another way. So if I go to your home and say, okay, I'll give you the exact same amount of active power as before, but 0 reactive power. Okay, you have no reactive power, but the same active power. What appliance in your home doesn't work anymore? Any ideas? Any guesses? Why air conditioner? Right, so Chad suggests air conditioner. Why air conditioner? This is correct, but why? Right, motors, right? So anything with motors consumes reactive power. Okay, so if you look at a motor, well, again, this is something later we'll do in the class. You look at a motor actually consumes a lot of reactive power. Right? So there's something that spins, and this rotation is the fact that you have a motor and there's a synchronous speed to the motor, this thing will consume reactive power. So this is something we'll understand a lot better later in class, but right now is, right? So if you have a washing machine, right? If you have a washing machine, it consumes active power, right? It has to wash your clothes, but for it to work, for it to spin, actually, it needs reactive power. Air conditioning, your fridge, all those things. Whenever you have a motor, you need reactive power. Right? So reactive power is important for the system once it has something to do with voltage. Important to some load that needs reactive power. Right? So, a lot of your home doesn't care about reactive power, that's true, but still a lot of appliances still do. Right, so this is right. So this is a good lead up to something called a power factor. Right, as we said, right, we want to think about how much of the apparent power goes to real active power, how much apparent power goes to reactive power. Then to do this, right? So to do this again with a single number. Okay, so engineers, you figure out, are very lazy. Right? Whenever we want to talk about something, we want to talk about it in a single number. That single number should be actually normalized. Okay, so these are the quantities we like. Okay, we want, right? So we just want one number that's sort of normalized to 1, or that we can talk about. So in power, there's a very good number associated with this. This is the cosine theta of the angle. This is the cosine of the angle. Because if it's sort of all active power, you have cosine of the angle. This is cosine of 0. This is 1. Okay, so a power factor of 1 tells you that all the power is in active power. Right? This is a good. This is sort of a, sometimes this is a requirement when you consume a load. Okay, this is called active power, so it's called power factor. Right, then if there's sort of all reactive power, you have cosine, let's say theta, this is cosine plus minus 90 degrees, this is 0, so that means you have no active power. Okay? So often this power factor, cosine of theta, is an important design criteria. It's important design criteria. Okay? So for example, you have a computer adapter or laptop adapter. You have a power factor of around, say, 0.8 or so. Right? Sometimes worse. I think Apple a few years ago had a power factor of like 0.65 or something. Right. So when you look at right, so when you look at this kind of power factor, this is the important design criteria, or important sort of a single number that characterizes how much active power was the reactive power. And for something like a power adapter, right, your computer needs active power. And once it gets to DC, you consume the active power. Then the power adapter, you want a power factor like close to 1, right? So better adapter if the power factor is closer to 1. Of course, that's a trade-off between how close you can get to 1 versus the sort of the cost of your adapter. But this is often a useful number we have in the system. Then, right, since we really want to get a single number, so we look at cosine theta. But the bad thing is cosine is a even function. So it doesn't care whether the angle is positive or negative. But we sometimes may want to tell whether it's a positive, right? We want to tell whether it's a positive angle or whether it is a negative angle, right? So this is what we want to do in practice. So the way we do it is to say, right? So then we basically, if the current is lagging, right? So then what we want to say is that, so if for the voltage, or let's just be more specific, if theta is positive, we say this is a lagging power factor. So here, for example, we say something like 0.9 lagging power factor, lagging. Then if theta is negative, this is a leading power factor. We'll say there's something like 0.9 point factor lead. Okay. Right, so this is just something that we use to denote the sign of the angle, right? Since the power factor doesn't account for the sign, cosine is being even function, so we just add a lagging or leading to talk about the sign of the angle. Right, so often you'll see, I have a load that consumes 0.9 power factor lagging, that tells you what the sign is. So these are sort of more terminology or convention in our cases. Right, so if you look at reactive power, right? So let's go back to the question of, why do we care about reactive power? Right? Well, can we just ignore it? And the question is, not really, not really. Because often your load will have inductors. Okay, so load or loads can have inductors. So these are mostly motors. Right? We have motors, you have inductor. So then this means I have a reactive power, I consume reactive power. Consumed by the load, right? By the load. But then your people only pay, right? So but customers actual power, right? So if you look at your bill, it's kilowatt hour. It says nothing, right? For billing purposes, it's true that you're not getting billed for reactive power. It has nothing about, kV, kVAR or something, right? It has nothing to do with those units. Right? So that's the right. So we still care about this reactive power, right? Even though we don't pay for it. Right? Then if you consume too much reactive power, what happens? Well, if you consume too much reactive power, then what happens is you need, so this leads to more losses, for example. Okay, on the wires. Right? So why does it lead to more losses on the wires when you have more reactive power? Well, so if you look at, let's say you have a wire, let's say you're passing some complex current. You're passing some complex current through it. What is the loss here on this resistor? If I pass a current? Suggestions, right? So I have some complex current, a current with magnitude and right, not a phase. I put this through a resistor. Then what does this do to the loss? How does this scale with the loss? Right? So normally, as for a DC circuit, it's I square R. So what is the equation here for loss through this resistor?
Isn't it the same because the resistor is in phase with the voltage and the current are in phase?
Right. So it's not I squared, right? It's not the complex current squared. Right? It's not the complex current squared. Rather, it's a magnitude squared
Conjugate.
Right. times R. Right?
Uh,
This is magnitude squared, right? So it's in phase, right? So the imaginary part will all cancel out, or the angles all cancel out. So it's a magnitude squared. It's R. Right. So that's the loss you have. So the problem is, right? So if you have a reactive load, I need to supply the load. So I may need a current with a larger magnitude. But this larger magnitude leads to a larger loss if I have a resistive component in the wires. Okay, so a larger reactive power, even though we're not paying for it, it may lead to a larger loss. Then we need to compensate with by sending more active power, right? To compensate for this loss, right? So but this power gets lost in the wires, right? So this is some inefficiencies in the system. Okay, so this can lead to additional losses. Also, we have transformer capacity. Are as in the apparent power, right? The apparent power. Okay, so it does create a impact on the network. Can lead to larger losses, take out some room. Okay. Right. So then this is the idea. So we still need to care about it. We still have a reactive power. So this is sort of the last thing again to emphasize that active power, reactive power, even though we write a sine and cosine, this active power is really the average. Okay, so this is really the average. This is the time average. Whereas Q, this is the size of the oscillation. This is the size of the oscillation. Okay, so this is, again, just they're not exactly the same, right? They're still different. Okay. Right. Okay, so let's see. Okay, so let's look at the power balance. So we'll try to get to a more important thing, right? So if you look at this, the problem is reactive power. Here I said a lot more losses, take up capacity. This is true, but not the biggest issue, right? So more loss is not a huge issue. It's nice if the loss is low, but the the 5% more loss will not kill us, right? So let's try to get to a point where reactive power impacts something like a voltage. Right? Let's try to get to that point. So to do that, we have to look at the power balance, right? To do power balance. So active power balance is actually quite simple. Quite simple. There's very clear sources and sinks, right? Something's producing power, something's consuming power. And this is conservation of energy. Okay, so active power is often easy to do the balance. You know who are the generators, you know who are the loads, you add them together, it must be equal, right? The power produced must equal to the active power consumed. Reactive power is a little bit trickier, it's slightly more tricky, slightly trickier. Right? Because here, it is true that reactive power produced needs to be reactive power consumed. But then the idea, there's sort of many sources for reactive power. Okay, so we still have conservation of power for the reactive power. It's true that we need to balance them out, but then often the source and sink are not, all that easily identified, all that clear, right? So we can sometimes, we can have leading or lagging, we can have different types of reactive power, right? So these are the, so it's not as clear cut as before, but still we can do some calculations, right? We can still do calculations with them. Okay. Right, so we can still do calculations, right? So some useful equations summarizing what we developed before. As load, right, always consumes active power. That's our terminology. Then reactive power is consumed or produced by a, by an inductor, capacitor, or a source and load, right, depending on the sign of the angle. Right, so then if you look at power balance, basically still everything has to balance. Still everything has to balance. But then for reactive power, it's just that the source is not depending on the angle, right? There's this sine theta, depending on the angle being positive or negative. This Q coming out as source or sink could be positive or negative, okay? Even though it still has to balance all across the network. All right, so this is our Q. All right, so here again, sometimes we'll say things like Q loss. Right, we'll say things like Q loss. Again, this is a loss that's not going to heat. Right, this loss doesn't get translated into heat. Okay, this is just, we just use Q loss because we want to think about the transmission line being inductive and the inductor consuming reactive power. But this is not something that will end up as heat outside in the environment. Okay. All right, and also you can have a load that's capacitor, right? You can easily have if you have a capacitor as a load, the source has to consume reactive power. Right? So all this thing can happen. It's not as clear cut as active power. Right? It's not that clear cut. Okay. Any questions here?
So then, so like a factory with a lot of motors and stuff, does the power company put more capacitors and stuff on there in order to kind of offset that? Or, I mean, do they just send in more active power and it gets bled off, or how does that work?
Right, so we'll add capacitors. We'll add capacitors. So really what happens is you have a factory, right? You have a lot of motors or heavy manufacturing. Then what we do is we'll add capacitors close to the load. We'll add capacitors close to the load. And often what you see is, so if you draw this out, is, right, so for a large inductive, for large inductive load happens as, right, let's say you have a load that's heavily inductor, right? So let's say you have a load in parallel and you have a large inductor. Then what happens is normally you get this is a sort of tunable capacitor or a variable capacitor added. And this is a variable capacitor we add to the load. And what happens here is basically you have a capacitor, and then this will change the capacitance of it depending on exactly how many machines you're running in your load. And then you try sort of, cancel as much as you can out, right? You'll try to produce reactive power close to the load through the capacitor, such that you don't need to send a lot of power along the line. Okay, so this is a tunable capacitor here. Right, so what's the reason of adding this close to the load and say not closer to the generator?
You don't want to add all that reactive power to the rest of the line, right?
Right, so your line consumes reactive power, right? So you may as well add it close to the load and not have to go through your line, right? So not have to, lose reactive power on your transmission line, right? So your transmission line are largely inductors, right? The transmission line are largely inductors, so that will consume reactive power. So may just well add it close to the load, right, whenever you're consuming this. Okay. Any other questions?
So just to clarify,
Right.
by adding that capacitor, we reduce the loss of reactive power in the transmission lines.
Right, we don't have to send as big as a current.
Okay.
We can send a smaller current because what we can do is this whole thing together appears as a smaller reactive load. Right, this thing appears as a much smaller reactive load. So I don't need to send as much current to you.
And if we didn't add the capacitors, would you also just be like messing with like the surrounding like components, like because you just have this big inductive load, wouldn't that like mess with other stuff? I don't know, like by throwing off the like phase of the like current and
Right, yeah.
voltage.
Yeah, right. So if you did not have this capacitor, what happens? This inductor, right? This sort of will basically will pass this big oscillation back and forth. And you sometimes you really don't want this oscillations to go back and forth. The reason is, right, everything we said is based on, we assume that's a 60 Hertz grid, right? It's a sort of perfect 60 Hertz grid. That's not the case, right, for the actual system. There are some so-called harmonics because you're not exactly 60 Hertz. Then now if you're passing this sort of big wave back and forth for reactive power, this sort of big oscillations, then that makes the other sort of the non-ideal thing, the harmonics, much worse in the system. That makes the harmonics much worse because you have this big oscillation. And then if things are not exactly perfectly 60 Hertz, you create this sort of little oscillations at higher frequencies. And that can mess up the rest of the system. As you know, grids typically don't like this sort of harmonics, right? So you want to cancel out. And that's why people complain that the Apple adapters are so bad, actually. It's, you know, it's one that's bad is for higher losses. Even if you don't care about that, there's actually a lot of high harmonics coming from these adapters because their power factor is not as close to one as you may expect.
So you said the power company doesn't charge us for it, but I'm assuming they track reactive power, or do they not even?
Oh yeah,
look
they're
at
not, right, so they track it. So this capacitor a lot of times is installed by the power company. Reactive power comes close to your homes are installed by the power company. And if you're a large enough load, they force you to have a pretty good reactive power factor. So UW being a very large load on the Seattle grid, and we appear to the grid as a single point of connection. As I say, we appear to the grid as a single point. Our power factor is quite well regulated. Right? So for us, I think we have to be like 5% or 2% around the power factor of what? Power factor of what? We are actually tracked on that. So City Light looks like our power factor, and we're not close enough to one. You know, somebody gets a phone call and saying what's going on with your load. So there's sort of a team at City Light, I think, that only deals with UW. And we're such a large load that something we do will show up on the grid. So we're monitored quite closely. Right? And so we have capacitors. We switch capacitors to make sure we have a fairly good power factor. So if you work in the power plant or you work with the UW facilities people, we do this kind of switching. Okay. Any other questions? Okay, all right, so we have 15 minutes left. So I don't want to rush through the calculations because I want to do them fairly in detail. So let's end the class here today. The next class we'll pick up, we'll do the calculation. That'll take about 20 minutes to do, then we'll go to power electronics. But today we'll end here, and this should give you enough information to do your homework. Okay, all right, so I can take more questions, but if you don't have questions, then I'll see you on Wednesday.
Thank you.
Thanks, sir.
Thank you.